So hello students, today we are going to discuss about a very important concept of stoichiometry, that is limiting reactant. We have studied in stoichiometry mole concept various laws of chemical combination, in which the most fundamental one is law of definite proportion. That means if reactant reacts, they react in a fixed mass ratio, no matter in what mass ratio we mix them. So reactants combines in a fixed mass ratio irrespective of the supplied mass ratio. Then what happens if we mix the reactant in a mass ratio other than stoichiometric mass ratio? One of the reactant will be exhausted, will be consumed completely, and one of the reactant will be left unreacted to some extent at the end of reaction. That means if they are not in a stoichiometric mass ratio, then part of one reactant will be left unreacted at the end of reaction. So the question is how to determine which reactant will be remaining unreacted at the end, which reactant will be consumed completely at the end. That is the whole concept we are going to discuss in this video, that we call concepts of limiting reactant. So first of all, what is limiting reactant? And moreover, this limiting reactant poses a lot of problems in solving the problems of entire physical chemistry if we are not very clear and not very confident about the concept of limiting reactant. Then even if we know each and everything, we may do it wrongly due to a stoichiometric problem, due to the lack of knowledge of stoichiometry and especially limiting reactant. So limiting reactant is a very important part of the stoichiometry. So let us first define what is exactly limiting reactant. Limiting reactant, as I have already said, that if the reactants are not supplied in a stoichiometric mass ratio, then one of the reactant will be reacted completely and another will be left unreacted at the end to a small extent. So basically, a limiting reactant is the reactant that reacts completely at the end of a reaction. To illustrate it, let us take a very simple example of a chemical reaction. Suppose we heat carbon with sulfur, they combine to form carbon disulfide. According to the law of chemical combination, 1 mole of carbon combines with 2 mole of sulfur to produce 1 mole of CS2, carbon disulfide. 1 mole of carbon corresponds to 12 gram of carbon. 2 mole of sulfur correspond to 2 into 32, 64 gram of sulfur, and if they combine, they will produce 64 plus 12, 76 gram of carbon disulfide. So this 12 gram and 64 gram are the stoichiometric mass ratio. In this ratio 12:64, carbon and sulfur will combine. So this we call a stoichiometric mass ratio. What happens if we don't mix them in this ratio? What happens if we mix them in some different ratio, different mass ratio? For example, let us take a case where we supply say 5 gram of carbon and 8 gram of sulfur. This is now supplied mass. We want to know which reactant will be exhausted completely. That is, which reactant is the limiting reactant, which reactant is in excess, and what will be the mass of product. The best way to find out the limiting reactant is, first you write the stoichiometric mass as I have written, and then you write the supplied mass as I have written. Then try to make one of the supplied mass. Try to make one of the supplied mass equal to a stoichiometric mass by multiplying the supplied mass with a constant factor. Means either you make this 864 or you make this 512. By multiplying the given masses by a constant factor, it is easier to find a factor of 8. So 8 into 864. So what I am going to do, I am going to multiply it by 8 in order to make this mass 64. So if I multiply it by 8, now carbon will be 8 5 the 40 gram and sulfur will be 8 8 the 64 gram. So now we have been supplied mass in 40 into 64 mass ratio. 64 is the stoichiometric mass of sulfur and a stoichiometric mass of carbon according to that is 12. So if we make one of the mass equal to a stoichiometric mass, other mass can be either greater or less than the stoichiometric mass. Here we have obtained 40, which is greater than 12. Means we have been supplied 40 when the requirement is only 12. So with 64 of sulfur, we have been supplied 40 of carbon and we require only 12. So this is in excess and sulfur is the limiting reactant, since 64 of this will react with 12 and the remaining 28 will be left unreacted. So once again, write the stoichiometric mass, write the supplied mass, try to make one of the supplied mass equal to a stoichiometric mass by multiplying with a constant factor. I have multiplied this supplied mass by 8 in order to make sulfur 64. Then the other mass, if greater than the required stoichiometric mass, then that is in excess. If that is less than the stoichiometric mass, then that is the limiting reactant. Next, once we know the limiting reactant determines the mass of product since it reacts completely. So now we have limiting reactant here, sulfur. So let us work out the mass of product. We know that 64 gram sulfur gives 74 gram CS2. So 8 gram of this sulfur will give 74 divided by 64 into 8, so it is 8, 8, just 64, 4, 2, 4, 19, so it is 9.5 gram of CS2. So our product mass is 9.5 gram. What happens if we determine the limiting reactant wrongly? Suppose if we commit some mistake and we determine the wrong limiting reactant. In this case, suppose somehow by doing some calculation mistake, we obtain carbon as the limiting reactant. What would have happened? Then we would have calculated the mass of product using carbon. So here 12 gram carbon gives 76 gram CS2. So 5 gram of carbon will give 76 upon 12 into 5, which will be equal to 76 into 5 divided by 12, so it is 31.66 gram, which is wrong. Why? Our total mass of reactant is 5 plus 8, 13 gram. So in no case the product can be greater than 13 gram, otherwise the law of conservation of mass will be violated. So it is 31 gram, which is greater than the mass of sum of the masses of reactants. So it is wrong. So if we have determined the wrong limiting reactant, the answer will tell us whether the limiting reactant we calculated is correct or incorrect. So the first thing is to find out the limiting reactant, and then limiting reactant determine the amount of product. So let us try one more situation similar to this. Suppose we have given a question that what maximum mass, what maximum mass of PCl5 can be obtained by reacting 3 gram of phosphorus with 15 gram of chlorine gas. Atomic mass of phosphorus is 31, chlorine is 35.5. So we have been given the reactant phosphorus and chlorine. So first of all, what we will do, we will write the balanced reaction. So white phosphorus reacts with chlorine to give PCl5. So 5, 2, so make it 4 phosphorus. So 4, 5 are 20 chlorine, so 10. So 1 mole of this combines with 10 mole. 1 mole of this will weigh 31 into 4, so it is 124 gram, and 10 mole of this 35.5 into 2, 71 into 10, 710 gram of chlorine. So 710 gram of chlorine will combine with 124 gram of phosphorus to give 834 gram of PCl5. So this is the stoichiometric mass. This is stoichiometric masses. Now supplied. So supplied masses are 3 gram of phosphorus, 3 gram, and 15 gram of chlorine. Now what we are going to do, we are going to convert this 15 to 710 or 3 to 124. So let us convert this 15 to 710. So multiply it by 710 by 15. So this mass will become 710, while the mass of phosphorus accordingly will be 3 into 710 divided by 15. So 7 3 5 the 15 and it is 5142. What we have done, we have made the mass of chlorine equal to stoichiometric mass, and now see Now see, oh, sorry. Now see how it compares with the mass of phosphorus. So mass of chlorine is 710, and then for 710 gram of chlorine we require 124 gram of phosphorus, and we have been supplied 142 gram. So for 710 we have 142 gram of phosphorus, but the requirement is only 124, so it is in excess. It is in excess. Phosphorus is in excess and chlorine is the limiting reactant. Chlorine is the limiting reactant. For this 710 requirement is 124, available is 142, which is more than the requirement. So chlorine is the limiting reactant. So we will be relating the mass of product from the mass of chlorine, not from the mass of phosphorus. Phosphorus is in excess. So 710, now calculate 710 gram of chlorine gives 834 gram of PCl5. So its 15 gram will give 834 upon 710 into 15. So it comes out to be 17.62 gram. 17.62 gram. That is the mass of PCl5. And if we find the wrong limiting reactant, if we determine the limiting reactant, say by somehow we determined phosphorus as the limiting reactant and we did the same calculation, we would have obtained the mass of product greater than 18 gram, which is the sum of the mass of reactant. So that is how we determine the limiting reactant in a chemical reaction, and its importance can never be underestimated. It is a very important part of physical chemistry. Everywhere we need to do a stoichiometric calculation, where we first need to know which is the limiting reactant so that the mass of product can be determined accordingly. So some practice is required. So I'm going to do some more practice on limiting reactants. So let us see some problems based on limiting reactant. Here is a problem that acrylonitrile, it's a compound, this is acrylonitrile, is the starting material for the preparation of a kind of synthetic fiber PAN. PAN stands for polyacrylonitrile, which is a polymer of acrylonitrile and can be made from propylene. by the reaction with the nitric oxide. This is the reaction, and you have been given balanced reaction, so you don't need to balance now, otherwise first you'll have to balance the chemical reaction. The question is, what mass of acrylonitrite can be made from 21 gram of propylene with 22 gram of NO. So let us work out in the same manner. We have 4C3H6 plus 6NO giving 4C3H3N plus 6H2O plus N2. So mass of this is 4 into stoichiometric mass, 4 into 12 3 is 36 plus 6 42. So it is 4 into 42 168. It is 6 into NO. Nitrogen is 14, oxygen is 16, so it is 30 into 6 180 gram, giving 4 into C3H3N, C3 36, 339 on 39 plus 14 53 gram. Supplied masses are 21 gram of propene, 21 gram, and 22 gram of NO. 21, which is half of 42. So let us multiply it by 8 so that this quantity will be 168. So this quantity is now 168 and this quantity will be 22 into 8. 22 into 8. So it is going to be 176. This is the supplied mass ratio. So for 168 requirement is 180. The available is 176, which is less than 180. So it is the limiting reactant. For 168, the requirement is 180 and we have been given only 176 grams. So NO is the limiting reactant, that is very close, and if we don't do it carefully, we may land up with the wrong answer. So once we know the limiting reactant, now we have the relation. So since 180 gram of NO gives 53 gram of C3H3N acrylonitrile, so 22 gram of this will give 53 upon 180 into 22. If we solve it, 53 into 22 divided by 180, so it is 6.4 gram. Just a moment. It is 53 the molar mass, so multiplied by 4 for 4 moles. I am very sorry. So 53 into 4, so 212. So it will be this into 4, so into 4 will also be there. So now 53 into 4 into 22 divided by 180, so it is 25.9 gram. 25.9 gram. .9 gram. Right. So That is how we do the calculation for limiting reactant. Let us see one more problem. The question is, manganese dioxide is reacting with hydrochloric acid, giving MnCl2, chlorine and water. The question is that if 29 gram of manganese dioxide is allowed to react with 45 gram of HCl, what maximum mass of chlorine can be produced? Again, it's a question of limiting reactant. We have to find out which is the limiting reactant. So, manganese dioxide reacting with HCl to give MnCl2 plus Cl2 plus 2H2O. So 1 mole of this is 87 gram. 4 mole of HCl will be equal to 4 into 36.5. So 146 gram. And that will give, so we are only concerned with chlorine. So that will give 1 mole of chlorine, which is 71 gram. The supplied is 29 gram of manganese dioxide and 45 gram of this. 29 is multiple of 87 is multiple of 29. 29 3 are 87. So what we do, let us multiply it by 3. It will give 87 gram here and 45 into 3, 135 gram here. So for 87 gram of manganese dioxide, now we have available 135 gram of HCl, but the requirement is 146. So limiting reactant is HCl. Requirement is 146 for 87, and for 87 the availability is only 135 gram. So it is the limiting reactant. Now 146 gives 71. So 45 will give 71 upon 146 into 45. So it will be 71 into 45 divided by 146. So 21.88 grams. So it is 21.88 gram. That is the required mass of chlorine gas. So one more practice. Here is a question again for limiting reactant. One of the components of fuel mixture on the Apollo lunar module, it is lunar module, involved a reaction with hydrazine and N2O4. If the balance reaction is this, what volume of N2 gas under STP condition would result from the reaction of this? The question is again related to limiting reactant. N2H4 plus N2O4 giving 3N2 gas plus 4H2O. This time we have to calculate volume of N2 at STP, so we require mole of N2. Balancing gives 2 of this, 3 of N2, 4 of H2O. So stoichiometric masses are 2 into molar mass of hydrazine is 28,432. 32 into 264 gram. This one is 28 plus 64. 28 plus 64, 92 gram. And here we have 3 mole. See, now I am writing mole because at the end we want mole of N2 so that we can calculate the volume at STP. Supplied 1100 and 1472 gram. Try to make one of this equal to 92. So, or let us, it is now bigger, 1472 is bigger than 92, it is not gram, it is kilogram, so mass is too much now. So what can be done? I think this 1472 is divisible from 92. 1472 divided by 92, yeah, it is. So 16 mole. It is 16 mole. Since 1 mole requires 2 moles, so 16 mole will require 32 mole. And the corresponding mass will be 32 into 32. Molar mass of hydrogen is 32. So 1024 gram. And available is 1100. So it is in excess. And this is the limiting reactant. N2O4 is the limiting reactant and the other one is excess. So the calculation will be done according to N2O4. Now 92 gram of this gives 3 mole. So 1472 gram will give 3 upon 92 into 1472 mole. So it is 16, so 48 mole. But this is for gram. Actual mass is in kilogram. So the same factor will come for the mole. So the moles of N2 produced will be equal to 48,000. So the volume of N2 at STP will be equal to 48,000 into 22.4 liter, which will be equal to 1075.2 kiloliter. So the concept of limiting reactant must be very clear and it is going to be very important. So let us try one more situation on limiting reactant. The question is when iron hydroxide, ferrous hydroxide is mixed with phosphoric acid, phosphate precipitate is formed. First is write the balanced reaction. So let us first write the balanced reaction. FeOH whole twice reacts with phosphoric acid H3PO4 to give Fe3PO4 whole twice plus H2O. If we balance for 2 phosphate, we require here 2 phosphoric acid, for 3 ferrous hydroxide. So it will be 6H2O. This is the balanced reaction. We have been given 3.2 gram of ferrous hydroxide and 2.5 gram of phosphoric acid. So first of all, let us know their stoichiometric masses. Ferrous hydroxide is 56 plus 34 90 into 3, 270. So it is 270 gram, and phosphoric acid 2 into 98, 2 into 98, so it is 196 gram. That is stoichiometric. Supplied 3.2 gram and 2.5 gram. So first let us know which is the limiting reactant. So it's better to make this 270. So let us make this 270. So multiply it by 270 divided by 3.2. 270 by 3.2 multiplied by 3.2 will give 270 on this side. On this side 270, sorry, on this side it will be 270 divided by 3.2 into 2.5. If we calculate it, it will be 270 divided by 3.2 into 2.5. So 210, 210.9. So for 270 the requirement is 196. For 270 the availability is 210, which is greater than 196. So this is in excess and this is the limiting reactant. So now we know that ferrous hydroxide is the limiting reactant. Next we'll have to relate the product with the limiting reactant. So molar mass of product will be 95 for phosphate into 2, 190, 56 into 3 for iron plus 190, so it is 358 gram. And this is from 270 gram of ferrous hydroxide. So from 3.2 gram it will be 358 divided by 270 into 3.2 divided by 270 into 3.2, so it will be 4.24. So 4.24 gram precipitate will be formed. There is one more situation, one more part of this question, that if 3.8 gram of precipitate is performed practically, what is the percentage yield? So the expected mass theoretically was 4.2, observed is 3.8, so percentage yield will be observed mass, which is 3.8, theoretical mass 4.24 into 100. So 3.8 divided by 4.24 into 100, so it is 89.56, approximately 90%. That even the limiting reactant is not reacting completely. So similarly, let us work out one more on this limiting reactant. Here is a question. C4, sorry, there is something wrong. It should be C4H9, C4H9, C4H9OH. Now it is fine. C4H9OH plus NaBr H2SO4 gives C4H9Br plus NaHSO4 plus H2O. 15 gram of C4H9OH reacts with this much gram of NaBr and 32.7 gram of H2SO4 to yield this much gram of this. What is the percentage of the reaction? Now we have three reactants. Let us work out. We have three reactant C4H9OH plus NaBr plus H2SO4 giving C4H9Br plus NaHSO4 plus H2O. It is the balanced one. Now if we determine their molar mass, so it will be 74 for this, 103 for this, 98 for this, and we need to determine C4H9Br whose molar mass is 137. Supplied is 15 gram, the other one is 22.4 gram, and the last is 32.7 gram. Now out of these three, which is the limiting reactant? What we'll do, we'll make one of this equal to the stoichiometric mass. So let us convert this to 74. Multiply this whole masses to 74 by 15. So it will be 74. 74 by 15 is now the multiplying factor. So 74 multiplying this here, 74 upon 15 is the multiplying factor. 74, the other one will be 22.4 into 74 upon 15, and the last will be 32.7 into 74 upon 15. If we calculate them, 22.4 into 74 divided by 15, it comes out to be 110.5. 110.5. The last one is 32.7 into 74 divided by 15. It comes out to be 161.32. 161.32. So for 74 gram of alcohol, we require 103 gram of sodium bromide, but available is 110, which is more than the requirement. So it is excess. We require only 98 gram of sulfuric acid. We have available 161, so it is in excess. So this is the limiting reactant. And now accordingly, we'll determine the mass of product. So 74 gram of C4H9OH gives 137 gram C4H9Br. So its 15 gram will give 137 upon 74 multiplied by 15. So it will be 137 divided by 74 into 15. It is 27.77 gram. Which is the theoretical mass. We have also been given a practical mass 17.1 gram, which is very less than the theoretical mass. So the percentage yield will be equal to 17.1 divided by 27.77 into 100. So 17.1 divided by this into 100. So it is 61.57. So 62%. So in this way, I complete this concept of limiting reactant, and I hope this will help you a lot. You will be benefited a lot because the limiting reactant is the first tricky concept of mole concept and we need to understand it very clearly. So thank you for this video lecture. In the next lecture, we'll be taking concentrations, manipulation of concentrations, which is another very important part of